All right, so Takeaway After Dark Summer School. Let's get this thing started. It's 7:06 already. I'm gonna have to boogie out for a couple of minutes in the middle of this, but that's when I'll transfer it over to Rick. I'm gonna start off the evening. Yes, Jason, I'll be hanging out with you guys on Thursday nights, but it's every other week. So yes, take a look at the Thirsty Thursdays with NTI is also another good time. So I've been hanging out there, been good to do. So Takeaway After Dark Summer School, episode 7. All right. And those of you that saw that John is missing, we're going to mix it up a little bit. All right. It's risky business. The parents are away. We're going to have a party. So, so Bruce Campbell's gone. Tom Cruise is in place. And we're going to go over circulator anatomy. We're going to talk about pumping away. I'm going to cover that part of it. And then Rickster is going to jump in with ECM essentials and talking about circulators. You tell everybody what that part is the second half of tonight.
Sure. We're still in the world where people will pull a circulator out of the box, especially in ECM nowadays, and the thing does all kinds of stuff, right? And there's plenty of people listening probably tonight, and definitely in the contractor world, is even manufacturers that don't really know, the simple way to understand which modes should be used for which application. And so we're going to cover that and give you lots of information and pictures and stuff that'll help you conceptually understand which one's best for what application. That's in a nutshell. So stay tuned.
There's so many different ones that are out there, and it's going to be like what to use, where, and why. So that's going to be pretty cool. That's going to be pretty cool. So, so for those of you that may be joining us for the first time, I still like to review it just a hair and go over the navigation around the control panel. So what the first thing you're going to notice here on your screen, the control panel, is this little sidebar. Is probably going to be on the right-hand side of your screen. And if your arrow is pointing to the left, then what you want to do is click on that arrow. Now, what's underneath that is a microphone. You guys are all muted from us on our software side. And then below that, you're going to see a question box. And below that, you're going to see a hand. So if you click on that arrow, expand it out, and then you're going to be able to see a lot more information there. And then because your microphones are muted, in order to talk to us, have any questions, and we don't do question and answer periods at the end. You got a question, you ask it right away, and we will bring it up immediately. So we see that. I got the chat section open right away. Rick is also looking at that at the same time. So type in your questions there, and we will either save it for the end, so to speak. Like when we get to the end of the night, sometimes there's a whole bunch of them that come flying in, but we try to go through them immediately as we see them going through. So if you understand this, obviously, please go ahead and type anything in there. I got one comment already in from Wheels talking about the Lorax here. Oh yeah, my Lorax. Where'd he go? Oh, he's over there. I can't get him just now. Otherwise, I don't have a long enough cord here on the headset. So I'll get my Lorax out in a little bit for you there, Rickster. So,
hey, Dave.
Yes, sir.
Can I throw out a little plug for you guys and some people who are actually attend these webinars? Can you talk a little bit about the Eastern Energy Expo virtual event that's going on this week?
Oh yes, actually, it's for the entire month. So
it's the month. I'm sorry. Yeah.
Yeah. So Eastern Energy Expo, it's a trade show that's been a combination of a couple of different organizations, AREE and the OESP group, and I believe there was one more, and I can't remember off the top of my head. But that show was slated back in May, which obviously then it got postponed until I think it was the middle of August. And then we went online instead for the entire month of August. So with the Eastern Energy Expo, it is a virtual trade show. So just do a quick Google search for Eastern Energy Expo, and you'll see the virtual show about there. There's live webinars going on. I'm doing a bunch of them. John Barber's got a couple of classes going on. A lot of other manufacturers are doing classes, and there's also recorded webinars that'll be there, and virtual trade show booths. So go ahead and take a look at the different booths that are there, because you can also make appointments and have conversations with the manufacturers, because they're still, bringing the best of the best in the company, right? Every trade show, every company brings the best people they have going to them. We can't do it face to face, but if you do it online, you can still talk to that individual person. So, so you can see all that. So that's going on for the entire month. The entire month. I did a webinar yesterday for them. I've got another one tomorrow that I'm doing on circ sizing, and tonight is their virtual dinner tonight, awards dinner, which is going on, and that's why I said I got to bump out and jump into that one for a couple of minutes, because I'm also on the education and training committee. So,
Do you have to change your outfit then?
no, I'm gonna stay the way I am. They know me over there.
Yeah.
So I'm good that way. So I was trying to get Rick to get into the long sleeve dress shirt and socks, but he wasn't going for it whatsoever, like Tom Cruise here. So so I
No.
could change into that real fast, but I don't think that'll go well over an awards dinner. So so good event. It's still trying to keep what they, their whole goal with OESP is still the training and education part of it. So I'm excited about that part. So it's been well received so far. All right, so let's get this thing started, and let's quickly talk about some circulator anatomy here. And I'm talking about the standard AC circs today. And just want to talk about some of the guts on the inside. Some of us never see them, never take them apart. And I got this drawing from engineering one day, and I just thought it was just kick ass to really see what's inside one of these things. Now, I have in my toolbox up at the factory, I have actually a couple of cutaways of these circulators so I can see inside. So I like to talk about a little bit of the anatomy here. And you may hear us talk about, the cartridge, or as I like to call, what's technically called is the rotor. All right. And then this part, the motor here, is actually called the stator. So your electricity goes across into the windings and creates an electromagnetic field, which then this stack of metal here grabs onto that electromagnetic field that is created here and spins. So it's not a direct couple. It's a wet rotor. It's not directly attached. The motor's not directly attached to it. Now the impeller is directly attached to the rotor part of it, but this stack of metal plates is what grabs onto that electromagnetic field and starts spinning. Now, what you'll also see, now if you look at this picture here, and you can see this little outline and this little dip here comes around, this is your cartridge. And I know most of you here have taken a circulator apart and pulled the cartridge out at one time or another. Years ago, back when we used to have our fastest hands competitions, or you just took it apart because you wanted to. So what you'll notice on the outside of that cartridge is right here, these metal rings, aluminum pinch rings that are on the outside of it. Right underneath those pinch rings are the bearings. So there's one here and there's one over here. And they pinch right here. You'll see these are the rings that we're not showing you the cartridge, but there's the ring. There is your bearing. Whoops. So your bearing here is clamped down. The bearing doesn't spin, but the ceramic shaft and this piece of yellow here is graphite. So we have ceramic shaft riding on graphite. It's not a ball bearing. And that's what is allowing your cartridge to turn around, to spin. So one of the other things I wanted to point out when we're looking at the cutaway of this circulator is this ceramic shaft. So the ceramic shaft is hollow. And on this side here is obviously where the water is, right? So here's our hydronic water. This is the inlet side of the circulator. And I know that because, one, you don't need to look for the arrow. All right. What you do is you consider what is today. What's today, Rick?
It's hump day.
It's hump day. So you always take a look at a circulator, all right, and you'll look for the hump. And where the hump is always your inlet, because a lot of times these are up against the wall in the back of the boiler room. You can't see it. So that is your inlet side. So here, this was a pretty cool design that we did. And if you notice, this hole is really tiny on this side, and then it flares out inside the ceramic shaft and goes all the way down to the very end. The purpose to this, to the hollow shaft, is to introduce water into the cartridge to flood this cartridge, and then at the same time push air out. And that's important because we do not flush water in and out of these things all the time. Water goes in on day one and typically stays in there. If you've ever picked up a cartridge and rattled it and shook it around, it sounds like something's loose inside here. And there's this little tiny, looks like a baby aspirin that we put in here. It's a lubricant. And when it gets wet, it dissolves and coats all the materials on the inside here to help quiet it down and keep it quiet. So water goes in and it doesn't come out. And that's because of the shape of that hole on the inside of that ceramic shaft. So that's an important thing. And that's also why we always say we want to see motors horizontal. You turn around and take your motor and point it vertically, point it up. Well, what could happen is very easily to get air trapped up here, and you'll burn out that top bearing because we need to have the water to help lubricate and cool that bearing down. And if it's not getting any, if the air gets stuck in here, I can't push it back down again. Now, I know we say in our instructions that you can, as long as your PSI is up a little bit higher so that it can squish that air bubble down and push it out. I just do it just for safety purposes. Always keep your motor horizontal. That's just the way I like to do it. And same thing, pointing it downwards. You could still get some air stuck in this portion here, but also when you point it down, then you have a chance for any sediment that could trap itself inside here, and also the tolerances to your volute. So the outside here is what we call a volute, and the volute is designed very close tolerances to your impeller. So the impeller has a very close tolerance touching the volute there. It doesn't touch it exactly. It's going to get really, really close there. So these are, they're not interchangeable from one size to another. Each volute is designed around the impeller, and we'll talk about impeller designs in a couple of seconds. So that's your cartridge part. Then there's the dirt seal here and water seal, where we try to keep everything on the inside. Here's our discharge side, and where we have our check valve. There we go. I got one floating around. So here's our IFC, internal flow check, that pops in. Of course, just O-ring down always, and make sure we have a little machined groove right there. And right there goes all the way around on the inside. And when you look at your check valve, you're going to see this little wing sticking out. There we go. There's the focus. You see those little wings sticking out? Make sure you get that to snap in. When it snaps in, it's all the way in. Please do. You might say, well, where's it going to go? I've seen them come get out dislodged and go down a pipe about 6 feet until it hit an elbow, and then get lodged into that elbow, and the customer had no idea, contractor had no idea what the heck was going on, why he couldn't get any flow out to his system, because the check valve was stuck and it was not allowing flow. It got turned around at that elbow. So make sure you hear that click. Make sure you want to use the check valve when you go to stick it in there, because when you go to get it out, you never get it out in one piece. So so don't test it. And I believe it's been since 2006 that all of our circulators have been machined to accept an IFC check valve. So even if you've got a circulator that does not have one, and if you need to add one, or you got an old flow check that's hung up, corroded, whatever it is, you want to hang it open and get it stuck in the open position, instead of changing that, maybe put one of these in instead of changing out the big old flow check you have on the system. So, but you can lock it in the up position so it doesn't shut down on itself again. You never want to double check a system. So that's parts of the motor part of our circulator and our impeller. But now I want to talk about the impeller design. And there's a lot of different designs to the impeller themselves. So circulators will look the same on the outside. The motors will look the same on the outside, but there's a lot of differences when it comes to your impeller. And so your impeller, what tells a circulator what it does is the design of the impeller. So what you see here on the right-hand side is a 007, considered what we say is an open-faced impeller. There's no facing on one side of it. Whereas, say, a 0015 or our ECM circulators is a closed-faced impeller. So where I don't see the vanes, it has a cover, so to speak, on the outside of it. The difference between those two types of impellers is typically an open-faced is going to be a high-flow, low-head circulator or impeller, and a closed-face is typically going to be a high-head, lower-flow impeller. And water always enters into the eye, right into the center of the circulator itself, of that impeller. So water goes into the eye, same thing here. Now, when you look at an impeller, this impeller does not spin in this direction. It doesn't scoop the water. This impeller's actually spinning in the clockwise position. The water enters into the center here. The vanes are close together. They get further apart, and the water kind of gets slapped out as this thing is spinning. Now, in a standard AC circulator, we're running at 3250 RPM. So very high RPMs that these things are running at. And as this is spinning in this direction, it slaps it out. And when you look at an impeller that's inside of a volute, they're not perfectly centered. They're offset. And as you see here, it's closer to one side as it gets to the other. And with the vanes and the volute is when we start developing our differential pressure in here. Okay. And then being able to move water throughout our system itself. So the thicker the impeller, so you see your 007, all right, the vanes get kind of thick, all right. The thicker the vanes, the more flow you also get out of that circulator. And then the larger the diameter, the higher the head the circulator is going to do. All right, so those are the design criteria. So that's what happens when we design a new circulator. We will design an impeller, then match up a motor to it, and then go from there. And when we take a look at our pump curves, let's take a look at those single speed circulators for the moment, and all of the ones that are out there. So these are all our 00s out there. Lots of different designs. Started off with the 007 back in 1971, all right, down here. Was the very first one that we made. And then after that, we came out with the 005. And then the third one was the 006, what ended up being a mashup between the 005 and 007 components made the 006. So the naming system of the 00s is irrelevant. There is no naming system out there. That's one of the things I asked 8 years ago when I came on board. I said, there's got to be a rhyme or reason to it. And there is none. There is none. There was no rhyme or reason. 007 was first. And yes, the product manager at the time was a James Bond fan. That's why it got named the 007. The 005 came out shortly there, a couple of years later, because we needed something to compete on pricing. We barely sold any. But the 005 actually followed suit, is in size, and it was less than the 7. But then when we did the mashup between the 5 and the 7 and came up with the 6, we were like, oh man, that rule's all out of whack now, so let's not bother with it. Question comes through, did the 004 explode? The 004 was a very short run circulator. It was an OEM spa pump. So it had nothing to do really with our plumbing and heating industry. It was designed for a spa company. And then instead of trying to sell it on our own, we just discontinued it and never used it. And we've never had a 001 or 002. If we did, your head would explode. You're like, well, what's it going to do? So the rhyme or reason that we follow now for naming our circulators is what number's next. So if we were to design another 00 AC style circulator, it would be called the 0016 because that's the next number available. So if you notice, you look at this chart and you think K is going to be the highest number out there. No, it's the 0013. The 0014, which is circulator L, actually has 3 circulators bigger than it. So the naming system just doesn't, if you need a bigger circulator, doesn't mean you go to the next number. It's just a different design of the impeller, different design of the motor, different parameters that the circulators are going to do. So if you take a look for a second at circulator J, H, E, B, those are high flow, low head circulators. Then we come across and look at K and I and G and F and D. They're high head, lower flow circulators. All right. Circulator L, the 14, is kind of a mashup in between the two of them. Circulator G is our 009, usually used in a drain back solar style system where we are actually pumping up to something. So when the solar system drains back, we got to pump it back up to the panels. So very high head circulator, but very low flow. When you look at an impeller of that, it's about a 1/4 inch in diameter, but I mean in thickness, but the impeller size is huge. All right, when that 009, where your 007 is about this big. So those are our big differences. And so we design the impeller, then create the curves with a flow meter, pressure gauge on the discharge side, slowly tweak, open that valve, take the readings and connect all the dots and make the curve. And as you've heard John say many, many times before, Circulator always works on the curve, never does anything different. So that's what we're looking at there. All right. So I am running a little bit out of time right now, and I want to go over pumping away with you. But I've got to jump out for a couple of minutes. So Rickster, are you almost ready?
I'm ready.
All right. So we're gonna turn this over to Rick real fast. Hang on a second. I got to give you your props here, Rickster. All right, so now we're going to jump over to Rick, and Rick is going to go over his ECM essentials. What I want to go over is our pumping away, and also using this display behind me when Rick finishes up. So I see we're about halfway through our webinar already. If you got any questions so far about any of that anatomy that I went through, please ask it. Let me pass this over. Wait, oh, we got a question here. If you multiply 0.06 times length of run circulator, does the pipe diameter make a difference? That is typically using your standard pipe sizes based upon some of the rules that we've covered before, Mark, where 2 to 4 gallons a minute is going to be 3/4 inch pipe, 4 to 9 is going to be 1 inch. That's where you can use that 0.06 times length of run to find your head loss. PEX is a different animal. All right, so PEX you want to check out with your PEX manufacturers. You're looking 100-foot run work the same as 1/2 inch pipe as 2 inch. No, the larger the pipe, the head loss goes way down. All right, so we're typically, that 0.06 is usually based upon max flow rate that pipe size can handle. So if you had 1/2 inch pipe, all right, 2.5 gallons a minute. If you're looking at 2 inch pipe, that's 45 gallons a minute. So that number would work 0.06 for 45 gallons that you'd be running through it. If you're less, then obviously the head loss goes way down. So we usually use that just as a safe, quick calculation for your head loss calcs. All right, let me, where am I? Here we go.
You need to give me the screen.
Yep, am.
I'm clicking on show screen and nothing's happening. Show my screen. There we go. Okay, groovy. All right, let me shrink some of this down, shrink that down, push that over, get rid of those things and open it up. All right, can you see the ECM Essentials screen?
I got you.
All right, well, let's take it. Dave, we'll catch you when you get back, eh?
I'll still be monitoring on the flip side here. I'm just going to have two things going at the same time.
Very
So
good.
don't mind me.
All right. Well, folks, understand that these ECM circulators actually need an input, right? They need something to tell them what to do, okay? Let me go back a little bit. So somebody, I said this at the beginning, somebody gets a nice fancy ECM circulator, they open it up, pull it out of the box, and it does all kinds of cool things, but there's a lot of misconception of what they actually can do and what they do. And that's what we're trying to make sure you understand. If you understand that these things need a particular input, then you'll say, okay, I need to be sure to give it that input. So that's what I want to focus on. Of course, we've had the temperature differential circulator. We call it a delta T. And then we have a pressure differential circulator. We call it delta P, and it makes sense. And we're going to mostly focus on the delta P product, understanding that either way will give you enough information to make a good decision on which way you would go with these. Just the main point I want you to get out of this slide is understand that they need an input, okay? So let's focus on the delta P, or the pressure differential circulators. And what I'm going to talk about right now is general statements. It applies to everybody's product, no matter what color they paint the pump, okay? A delta P pump adjusts to the changing hydraulic pressure differentials within the system, right? They can actually feel things, and quote, feel things going on in the system. That's what they do. There's no pressure sensors or anything. They're just feeling the hydraulic changes. And the way they're feeling it is the impellers in the fluid. It's connected to a shaft. The shaft's connected to the motor. And the motor and the control logic we put to drive that motor, it's a little drive, it can feel when things get, a little bit more resistive and a little bit less resistive. So that's how they respond to that, okay? They vary their speed, but depending on what mode we have them in, they'll stay in these things called operating ranges, okay? And I'll explain what that means real quickly. So for instance, this little line right here, that's a dotted line that I've shown you up here on constant pressure, that's not a pump curve, okay? We all know what a pump curve, this is your pump curve. This is an operating range, okay? Some people call it a control curve. Either way you want to call it, you get what I'm talking about, but it's not the pump curve, okay? So just, being a little picky on the terminology here. Generally speaking, again, this applies to everybody's product. You'll get a constant pressure, you'll get a proportional pressure, or you'll get a fixed speed of some sort. There's some variables on these two, and pretty much fixed speed is fixed speed. But these are all, like I said, general statements here. Now, when it comes to the actual modes of operation, that's where the headache normally lies, right? I pull this out of the box, it's midnight, right? And I'm at, somebody's place, it's New Year's Eve, and I'm trying to get the heat back on. Well, yes, let's get the heat back on, but out of this kind of setting and this kind of training, we want you to grasp what mode of operation makes the most sense without doing a bunch of math. I know we always talk about doing the math, etc., but I'm going to give you some general, rules of thumb that'll get you out of hot water or into hot water at midnight on New Year's Eve. That's kind of what I want you to get out of this presentation. Understand that some of these modes are manual, and understand that some of these modes are automatic. And I'm going to use these little icons, like this little hand here will be if I'm talking about manual, and I'll use this icon if I'm talking about an automatic. And I'll put those way up in this right-hand corner up here as we go through these slides. Now, generally speaking, this is a traditional AC, in fact, this is a good old 007 pump, folks. And we're showing you that it runs on a single speed, which happens to be a maximum speed. Okay, David mentioned around 4,300 RPM, right? So this is where the unit runs. Well, when we get into world of ECM, it's kind of the same thing, but slightly different. We have the ability to run at maximum speed. We have the ability with ECM to run at a minimum speed. And the coolest thing about both of those is that we can run anywhere in between. So understand the differences between these two curves, right? Look, this is all you get. This is a monorail, and this is where the pump will run, okay? The operating point will be where the system resistance curve meets the circulator performance curve. But when we get into this, okay, now we've got all kinds of different places to operate. So I want you to have a mental picture of what we're doing here as it relates to the differences between ECM technology and permanent split capacitor single speed application. Even if it was 3-speed, it wouldn't be anything like we're looking here. And you folks have all seen 3-speed performance curves, okay? Now let's talk about the mode of operation, which is fixed speed, okay? I'm going to get rid of this little thing that's in my way. Let's talk about a fixed speed and the system curve. Now, understand if I'm using the fixed speed mode, that's typical of like a zone circulator, okay? The cool thing about these pumps that Taco sells now is we have a lot of rangeability between min and max, right? But I want you to visualize what's actually happening with the operating point. Watch this little ball right here. If I was to take a zone circulator and manually turn it down, I want you to visualize what happens when I do that. If I turned it down to say 3/4 of the dial, this is where my new operating point would be. It's just going to follow the system resistance curve here. Okay, so I turn it down again, I turn it down again, etc. So understand that's what you're doing on a zone pump when you have the ability and an ECM technology to turn the thing down. This makes it great. This is where we can have, 5, 6, 7 different pumps all in one circulator, or say it this way, performance curves variable within one SKU. Okay, so I hope that makes sense to you. So let's show you some pictures and make sure you understand that zone pumping is still an appropriate mode of operation, right? People forget this. They buy these fancy ECMs and they think, well, I got to use one of these cool auto modes because I paid for it. No, you don't. There's plenty of applications where zone pumping is the mode you want to put it in. And generally speaking, most of these circulators, including Tacos, will come in one of the automatic modes. So you have to know what mode it comes in, and you have to know whether or not to pull it out of that mode and put it into a more appropriate mode that meets your specific application. Okay, so zone pumping, you understand what we're showing you here. Zone pumping in everybody's world should be something like this. That circulator is brought on when there's a call from a thermostat. And that thermostat is going to be satisfied by that circulator standalone. And when that thermostat's satisfied, it simply shuts the pump off. So that circulator will not have any zone valves downstream of it. It won't have any actuators or diverting valves or anything. It's simply going to turn on. In this case, it's going to come on. It's going to go all the way through the system and come back down through the return portion of the piping. So we just turn the pump on and off. So understand that the fixed speed mode is absolutely the appropriate mode of operation to do any zone pumping. The cool thing about having the dial on there is now we've got lots of turn down or controllability, which we never had before. Even 3-speed pumps did not really have enough controllability. Now, Taco, hence the dial, right? We call it like a volume dial on there. Now you can turn that thing down more appropriately than you ever could before. So hopefully that makes sense to you. Let's move on to a couple things here. I'll show you first, we're still talking about the fixed speed mode, right? And notice this circulator here has zone valves downstream of it. Well, understand this, I don't want to use this circulator in a fixed speed mode, right? But look down here, this is what I want to focus on. This circulator here is doing nothing more than pulling water out of this boiler, okay? Pushing it through this coil and coming back through, and there's the loop, right? So that pump is never going to receive any of the input it needs to make a decision to speed up or slow down because it will have no hydraulic changes coming back to it. So by all means, fixed speed makes sense for any of the heat exchanger applications. I'm showing you an indirect fired water heater. This could be a heat exchanger for snow melt system or something like that. Again, for the most part, the fixed speed mode will be appropriate for those. Boiler primaries, you folks that have sat on this Taco After Dark for a while, I've shown you this picture before when we're talking about primary, secondary piping and such. I'm just going to make the same note as I had before. Some of the boiler manufacturers and some of the small circulators have the ability to receive a 0 to 10 volt DC signal. It's like a third-party signal so that we turn the keys over to the boiler manufacturer and let them run the pump, but not all of them do. So my point is, yeah, if you have these two shaking hands, okay, then by all means use that. But not every application has that, not every product has it, etc. So I'm just focusing on the fact that if you don't have that signal and you have a modulating condensing piece of equipment, most of the time a more appropriate mode is the fixed speed. You don't want to use any type of auto mode unless the boiler is telling that pump to speed up or slow down. So what we've done, and we've done this in other sessions, is shown you how to more appropriately size that circulator. What we really want to do in a nutshell is stretch that delta T out as wide as this boiler manufacturer will allow you to do that. You'll get a higher overall system efficiency if you follow that general rule. All right. Again, this is just showing you the boiler primary as a fixed speed. It's showing you also the indirect again, just letting you know, look, over here we've got a system pump, and of course it would receive that feedback, so it wants to be in one of the automatic modes that makes sense, which we're going to get into right now. Okay. Let's talk about the constant pressure mode. Okay, this is kind of the North American mode of operation. Lots of things point to this being the appropriate mode for most of the North American designs. Okay, and I'll show you why. A picture's worth 1,000 words, but let's just show you that same bouncing ball. Here's an operating point. Remember, we've got an invisible system curve in the background here, right? So if I were to see zone valves close, say all the zones are open, it's running at maximum speed, watch what that bouncing ball does. Okay, notice that little hop that it does initially. Okay, it's hopping up because it's doing the normal thing any fixed speed pump would do. It's actually feeling that additional resistance, and it's doing a job based on coming back down to where you told it to be, right? Now notice it hops up and then it says, whoa, you told me to stay at a certain constant pressure. In this case, it's showing you that we told it 10 feet ahead. So just understand that that's what it's doing in the background. This is what, when you're standing in front of that pump and it's slowing down, you know visually, I'm showing you what it does. You folks that have already had the opportunity to use one of our 0018Es, you actually get to see this in real time based on the Bluetooth feedback into the circulator. But this is something we've used to teach on for years now. So I want you to visualize that. So when do we use constant pressure? Remember to look over here. It is an automatic mode. And you folks that have heard the term home run, I want you to understand what I mean by that. I have paralleled 3 different supplies and corresponding returns over here, right? And this header, this relatively short, fat header, I'll do that in quotations because Siggy's made that very popular, right? What we want is this header to be sized more in the realm of about 2 feet per second than 4 feet per second. That's another session. If you don't understand what I mean, we can get into that some other time, or pop it up as a question. Maybe we can do it after the actual setting. So we've got 3 zones here. Now remember, when you did Hydronics 101, you learned that when these zones are piped in parallel, that one of them will set the precedent for the pressure drop this circulator needs to overcome at any given time. So with that in mind, that kind of points the finger at constant pressure. Okay, so again, just understand that. Again, we don't have the time to go really deep into each one of these, but be sure to ask the question, and we'll take the time once we get through the actual session to answer some of your questions. Here's another view of that. Again, people have done this. Again, you see this in magazines. It's got a dedicated supply return that come all the way back to the boiler room. Okay, with in this case, it's kind of depicting flexible piping like PEX or multi-layer composite or some of those products that are on the market. So, but understand this, that one of these panel radiators, based on its load, its GPM flow, and of course, zoned run from supply and return, is going to be the greatest that this circulator has to overcome. And with that in mind, constant pressure makes the most sense for any of those home run applications. Okay. Again, we don't want to use an automatic mode like constant pressure as a boiler primary. Again. Now let's talk about proportional pressure. This is kind of the mystery mode. A lot of people have no clue what proportional pressure is all about. They don't even know what the word means. So I'm going to spend some time making sure you feel comfortable with that as well. And there's, it's primarily set up to do a certain piping scheme, and I'm going to show you what that means. But it's not just thermostatic radiator valves. And I'm not arguing with anybody here. I'm just kind of doing a little bit deeper dive and showing you where the calculation looks and makes the proportional pressure mode the most appropriate mode. Now, granted, majority of thermostatic radiator valve style pipings systems are appropriate for proportional pressure, no doubt about it. But there's actually some zone valve jobs that it would be appropriate for as well. And I just want to make sure I clarify that, okay? Here's the same operating point. Okay, same place we started. Now watch what the bouncing ball does when the zones start closing with this. Notice it gets that little hop as well. Okay, gets that little hop as well, and it kind of works its way down, but it's working its way down. It's working it just like constant pressure. It's working from the right to the left, but notice it's actually pitching down here. So it could get, a subsequently lower RPM. So by all means, proportional pressure mode will be probably the most watt conservative. However, that doesn't do you any good if it's not pumping enough to meet the need. So let me emphasize that. Make sure you get where we're going with that. So from the standpoint of understanding this whole proportional thing, it's actually not a big mystery. It's a simple algorithm that the manufacturer like Taco puts into the software of the pump. Okay, and we're just saying, okay, we're going to go from right to left and we're going to pitch down, but we're going to pitch down to what proportion are we going to do that at? Okay, so here's the way to figure it out. Take the low end, wherever it is on this 0 GPM, and follow it up to the high end, and take those two numbers and divide them by themselves. See, I'm going to show you all three of them real quick. 3.6 is this number divided by this number. 6.2 is here divided by 10.7. And then 7.8 right here divided by 13.4. Notice that my proportion here is approximately 58%. So you can take any brand circulator that's showing you any proportion, and you can simply take the low number divided by the high number at high speed and come up with the proportion. Not that that really means anything to you, but I just wanted to, it's like I said, proportional pressure has been kind of the mystery mode, and I want to kind of, shed some light on that mystery. I hope that makes some, sense to you. But let's get into the nuts and bolts about when is proportional pressure, or any of the automatic modes that are primarily proportional pressure. When are those appropriate? And I want you to kind of get a visual indication of that by these pictures. These are just depicting, piping schemes. In this case, it's two-pipe direct return. These are my little symbols for continuation. So let's say here's a mechanical room wall. Everything to the right here is in the mechanical room. So I'm standing in front of that thing. I'm looking at a pump that's got one big pipe going out the mechanical room and one big pipe coming back. Okay. I know this is a multiple zone system, and I know all the actual heat emitters or air handling units or manifolds, or in this case series baseboard. I know that's all out there, and all of these takeoffs are on this extended header out in the building somewhere. Hopefully that makes sense to you, hence the name extended header. Okay. Now, what you have to understand with this, whether it's a two-pipe direct return, or in this case, a two-pipe reverse return, is that I need this circulator to overcome the resistance, not just of the highest zone here, right? But also the resistance of this extended header under a design load condition. That's meant it's pumping to beat the band. It's trying to do everything it can. We have to take that whole thing into consideration. Here's another picture of an extended header application, and it's kind of where we get that whole concept of thermostatic radiator valves from. okay? Because we typically will have a pump that's running, 24/7 during the heating season, what we call continuous circulation, right? And these things need that in order to modulate open and close, right? So it's not going to be one of these panel radiators or thermostatic radiator valves that's going to set the precedent for this circulator. It's going to be one of those plus all the pressure drop that's associated with that extended header. Does that make sense to you? In this case, we've got the mains, we got the branches, we got the twigs, and all that has to be taken into consideration. Okay, so anyway, just want to make sure you understand that. I got a check mark for proportional pressure in this pump, but not in this pump. Okay. This is just showing you a traditional kind of European wall hung condensing boiler application. Okay. There's some people in North America that are doing this, but for the most part, not so much. Okay. Let's go through and show you real quick what that calculation kind of looks like. And I'm going to go really fast for the sake of time, but I think I can make the point and you'll kind of get where this actual decision comes from. The decision to go with constant pressure or proportional pressure, okay? I'm trying to tell you that for the most part, it's the piping scheme as I'm depicting. But if anybody wants to do the calculation, this is what you'll do. You'll do each of these terminal units. You'll say, okay, at a design condition, how much flow does it need and what's the resulting pressure drop, okay? See how I'm populating all those? You could take a look at all this, and I did a full design on this particular system. And I add all this GPM up and I get a number, right? In this case, 9 gallons a minute at 12 foot ahead is the worst case of all of these that I've shown you. I add the GPM together, okay, 75 GPM, but at what pressure drop? It's not going to be 12 foot ahead, because if you were going for constant pressure, that's what you'd set it on, and unfortunately, you would have made the wrong decision, okay? We've got some other things to think about. We have that extended header, don't we? We have the supply and return piping going out to the system. We have the near boiler piping that has to be a consideration as well. So we'll throw some numbers at it and just add it all up together, and you can see that we'll be at 32 foot ahead. In this case, we're going to do 12 plus 18 plus 2. That's how that number has come up, because remember, we've got to size this thing in case everything's calling and we're under a design load condition. Okay, so this is why once we know that these zones start dropping off, say this zone dropped off, these dropped off, well, I'm going to get a reduction in GPM. The pump's going to feel it. It's going to slow down. Therefore, you're going to get a resultant less pressure drop through the header. That's why the proportional pressure angle or pitch works good on these type of piping schemes, but not on the home runs. Okay. Typically, if you do a home run and you put in proportional pressure, there's many times that you will under pump because of the pitch of this. I'm just showing you that same job, 75 GPM at about 32 foot ahead. Okay. One point people misunderstand this is how do I know where to set this thing on our pumps? Well, again, you have to actually set it up for the angle. The angle takes you up at maximum speed to 36. But if you've done a good estimate on your pressure drop, you'll ride somewhere here at max speed and you'll work your way down there. Does anybody remember what our worst case zone was? Wasn't it about 9 GPM at what, 12 foot ahead? The only thing you have to make sure is that if this ramps all the way down, it'll still take care of your lowest zone requirement. So anyway, I know I'm covering lots of ground here, and I know Dave's not with me to catch the actual questions, and the way my screen is set
Oh, I'm
up.
back in, brother. I'm
Oh,
back
you're
in.
back in. Okay, is
I'm
there
here.
anything that somebody want to clarify? I've been talking like a banshee, but is there anything that you can see that we should cover?
There was a question that came in, but I'm not sure what it was in reference to, but it says indirect, very short run. Leave circ
Oh,
on very low for that, right?
well, it depends. Again, if you had a pump that had the ability to read GPM, you could actually set the pump on fixed speed to give you the GPM that you wanted. You can do that with our 0018. You can do that with our new 0034 series, plus series pump. So hopefully that answers that question. Yeah, short runs are typical, absolutely. But as long as you understand that normally on DHW, you're just turning the pump on. You want to get as much energy in that tank as quickly as possible, and you're not running on long continuous duties. So to bang that thing on and off fairly quick, and you might exceed 4 feet per second, but at such short intervals, it's usually not problematic. So hopefully that answers your question. So part of ECM realities is you've heard everybody at Takeo that you ever listen to talk about, especially when we came out with our product, is look, man, you've been misled if you think there's a magic button that's smarter than you are and can figure all this stuff out. There's absolutely no such thing as a magic button. Okay, so these pumps, we don't like to even refer to them as smart pumps because they're really not that smart. Okay. We have these things called adaptable type auto modes. Okay, Takeo calls it active adapt in one form of their pump. They just call it auto on another one. You know, Grundfos has got auto adapt. Dynamic adapt is something Velo just came out with, right? Armstrong's got something they just call auto as well. Okay, so any of these modes, and most of them, 95% of them, are always proportional pressure. So understand that in use any of those auto modes, you made a couple of decisions. I'll make that point here in just a second. So when is the appropriate time to use any of those auto modes? Okay. The first thing you have to understand is that the GPM and head have to fall into this wedge of operating condition. That's the first thing that excludes you from using auto anything. Okay, if your desired GPM and head don't fall into that wedge, do not use auto anything of any brand. Okay, that's the biggest mistake we've seen, people misapplying product. Okay, the other thing they have to understand is the piping support that I just talked about. The piping arrangement, it has to be supported by that. Extended headers for the most part only. Okay, if you've got a home run style piping arrangement, you can pretty much bag any of the auto modes. Okay, for the most part. There's a few exceptions to that, but very few. Okay. Understand that these are all proportional slopes, and some of these slopes are different. We have these things called fixed proportions, where, like I showed you, anywhere up on those three or anywhere within that range, you're going to be at one proportion in case, you know, typically 50%, right? If you get over to these variable proportions, one of Takeo's pumps, the big VRs and the little 3452 actually has a variable, right? Has a variable pitch. In this case, this low side is 50%. The high side, though, is 70%. The key to that, folks, is see if you've got like a big fan back here on the end of the wedge and it's kind of fat back here, and see how this is kind of fat back here as well. Those are typically fixed proportions. If you see any of them come back to a point like this, then those are variable proportional slopes, okay? And not a lot that you're gonna do with that, but it's just kind of nice, one of those nugget things that you kind of like to know. Um, More of the first things first here, again, you would never use any of the automatic modes. You got to remember these things are real slow to respond for the most part, with very few exceptions. Okay, so you're going to be either on continuous circulation or very long run times for these things to even work. These things have several minutes, I mean some as much as a half hour before they're ever going to do anything but other than start right in the middle of their run. Okay, next thing to acknowledge is always understand this, that they are always, probably 98% of the time, they're always uh, delta P operations, right? Unless you get into something like Takeo does with delta T, these are delta P pumps. They're only responding to hydraulic changes downstream. And guess what? You put this on as a zone pump, and it's never going to change its speed, even though you hook, line, and sinker drank the Kool-Aid that somebody else told you. It's not going to change its speed because you haven't given it the feedback it needs by the changing hydraulic differential within the system to ever help you do anything. So anyway, with those things, I hope those are just, we went through a lot really quick, but I want you to make sure that you got that. Now we're going to give this back to Dave. I like to call him the Big D, and there's his smiling face, and I'll pass it back off to him at this point.
Oh, crap. Where'd it go? Oh, there we go. All righty. Any questions out there, people? Please answer. Bring those questions in. Yeah, it was a lot of information really fast, but make sure you have some questions. Bring them into Rick, or to myself also at the same time. Yeah, it was a lot of info, but I know there's going to be at least a question or two out there from you guys out there. So bring them on up. Bring them on up. Okay, hang on. Change my screen. There we go. Excellent. Let me see here. Get the questions back. All right. Let me move the questions over to here. Excellent. So one of the questions that came in, Rick, before, why are you using 32 foot ahead and not 18, since that's the largest head requirement? I wasn't sure where that came into play there.
That's fine. If I went back to that slide, I've already turned it off, but if you remember, we had the head that we had to overcome. That was the highest zone. That was 12 foot ahead. And we had the head of the incidental pipe valves and fittings by the boiler. That was 2. And then we had what was the head that was required just for the extended header under design load condition? That was 18. You add those numbers together because in a linear fashion, head is cumulative. Okay, it wasn't a parallel. The parallel portions, we only took the highest head. But so that's where 32 came from. Again, I must not have made that point.
Okay, awesome. But yes, yeah. So when it was running in series like that from one section to the other with the pump, you need to add up the head from there. You don't
Yep.
need to add the GPM up. The GPM is what's needed for the whole thing already. We
Yep.
found that. But when you go from one section to another, you need to add your head up in there. So, and I guess that's how you got to the 32 foot ahead.
Now,
Awesome.
Chris has got one, just, checking on Delta T. You know what, Chris, I'll just cop to what John Barba said quite a bit. The Delta T is a great pump. In fact, I've got one on my system out in my garage right now, and I use it as a boiler pump, right, where I'm doing Delta T across the boiler's heat exchanger. But prior to that, for 4 years, I had it as a system pump, and it worked just fine, and mine is somewhat an extended header. It works just fine. So again, it's all in what you see as the value. But our Delta P pumps work really good as well. So that's why I wanted to say, I'll give you some information and you guys make a decision. So
Yeah, I mean, if you were to make the decision on which one to go with always, they can be interchangeable in a lot of applications, whether you go Delta T or Delta P. If Delta P, if we show some situations where Delta P shines. Delta T could do the same job there too. It's not going to be pressure differential. It'll still pump the water through your system itself. I think the biggest difference between the two of them, if you really needed to nail it down, is just the sheer cost, right? I mean,
yeah.
everybody always asks me, all right, you showed me all these pumps here today. Which one would you put in your house? All day, Delta T. Yeah, all day, Delta T. All right. But does every zone or every system call for the cost of a Delta T circulator right now? So I think that's where also the decision that you have to make based upon your system that you're working on and the customer, would they spend that much more money for a circulator, or will it give them that much more out of it? So my whole house is Delta T circs. Actually, my indirect is not Delta T. I have that set up as a 0015 set on high. But the radiant floor in my house is all set up as Delta T circs. I have VT 2218 for one zone. That's got a lot of actuators on it, doing almost 3/4 of the house. And then I do have a slab zone that I have a 006 VDT. I actually had to custom make that one. I took a VDT control out of a 008 and put it into a 006 in the garage and made it work here because the 008 was too big that I needed there. So
Yeah. Melik's got a question just about Delta P, generally speaking, and that just understand what Delta T is, right? That's the input to the circulator based on 2 temperature sensors. Delta P is just what it feels within the system, those hydraulic changes I talked about, valves opening and closing. And then Douglas has got one. Dave, you can take that one.
all right,
He's just
so
commenting. Yeah.
So Delta P meaning pressure, reading a pressure differential. So imagine this, Mike, when you have a zone valve in a system, you got 2 zone valves in a system, and both zones are open, and the circulator is running. when a zone valve closes, what's the pressure differential up against that circulator? Skyrocket, high, right? Super high. Pressure differential, can't pump any more water through it. Circulator will automatically slow down. And vice versa. Now the circulator slows down to only handle the one zone that's open. I got one that closed. But now imagine that circulator, that zone valve then opening up. The pressure's relieved. So now the circulator can move water through that. The pressure drops, circulator speeds up. It's the amount of water that it can actually fling out of the impeller. We call that a pressure differential, a delta P style circulators. So Doug says VT2218 works great as a zone pump on cast iron baseboard. Ramps
Thumbs
up
up.
and down to get the baseboard hot, then ramps down to keep it hot. Oh, definitely. Definitely. Yeah. It's like one of those, it's one of my little nicknames for it. We can't really call it that, but it's kind of like indoor reset. So can't say it's exactly indoor reset. It's kind of like indoor reset because it sees how many BTUs are being delivered out to the house itself. So based upon the return temperature coming back. So it works awesome. Yes. Cast iron baseboard, wonderful. Radiant floors, even better. So there's a lot of different things that it can do. You know, on that Delta T style circulator. Yes. Hang on a second. Still going on for a while.
That's okay. Congratulations.
Thank you.
Hey, Beth.
Yeah, so we had mentioned earlier about the Eastern Energy Expo and OASP, and Clark Kent had to leave the room for a little bit
Yeah.
because he was awarded the OASP 2020 Dan Holohan Award. So congrats to you, Dave.
Thank you. Thank you. So that's what I had to get out of here for a little while. So this was presented to me on Monday night, but I had to keep it quiet until tonight. So
they always spill the beans. Why do they do that?
And
yeah,
then Johnny,
well, no, they had to because it's not live at the show.
Right.
So
Gotcha.
they wanted to do it that way. So
and then Johnny White got the 2020 Lifetime Achievement Award. So congrats to you guys and Takeo for doing a great job.
Thank you. Thank you very much. Thanks, everybody. Thanks, Rich. Thanks, Mike. Yeah, complete surprise. Shocked, everything. I was out to dinner with a few of the guys the other night when they gave me the award, and it's probably one of the few times I'm speechless. I had nothing to say. I was just like, wait, what? What?
Yeah, Robert O'Brien shared a video, and you did look genuinely surprised and pretty stoked about it. So
yeah, it was pretty exciting. It was pretty exciting, you know, and knowing Dan for all these years too, and another fellow Long Islander, and doing training classes, and I used to try to get to as many classes as I can with Dan just so I can learn his craft too at the same time. It was just amazing, you know, and then of course learning a lot from John Barba, who's not here with us tonight, but I think he logged into the party over there before. So it was it's good. It is like I said, I get speechless. I don't know what to say. So thank you to everybody that's sending out congrats to me. Greatly appreciate it. Greatly appreciate it, man. I have a lot of fun doing my job. You know, it's you guys sitting in the room that make me, so to speak, look good when everybody's there because you know it's just fun. I enjoy what I do, man. I tell my kids this all the time. Find a job that you like to do because then you'll never work a day in your life.
Yeah.
So yeah, you know, and I enjoy this stuff. You know, never imagined doing this as Matt Spinks was saying. I didn't grow up in the trade like most of us did. Most of you guys did in here. You know, I went to New York Maritime. I worked on a steamship, worked in a machine shop. So I was used to working with my hands, but I didn't grow up in the plumbing and heating industry. But you guys accepted me in, and it was a lot of fun. It was a lot of fun learning this stuff, and now I've shoved all this stuff in my head over the last 25 years, and now I get to give it back, which is fun too. So.
Well, not only that, but you're just a good guy. So I'm happy for you, man.
Thank you very much. Thank you. All righty, shall we get back to work? Nah, let's start drinking. I'm kidding.
Cheers.
Let's see here. We had a couple of questions I think came in. Let's see here. If Delta P is the preferred on a multi-zone to allow for changes in head, how does that work with Delta T variable in the zones? Is done by managing the flow with the Delta P circ. So very good question that comes up quite often. Actually, not often enough, I think. Because we do kind of hammer that down pretty hard in looking at a zone valve system, changing pressure differential when the zone valves open and close. But if you put in a Delta T circulator with zone valves, obviously he's not looking at the pressure differential, but imagine this. All right, your system is completely off. You've got two zones out in the house, everything is off. What's the water temperature in the pipes? They're going to be 70 degrees, room temperature. All of a sudden, the air temperature in the room drops. Zone valve, thermostat turns on, opens up a zone. Boiler fires up to 180 degrees, and we're starting to pump water out. Obviously, not that quickly. So I've got 180 on the supply. What's on the return side? 70 degrees. Why Delta T? Circulator starts to ramp up and is going up and up and up until it starts to see some of that return temperature coming back. And as that return temperature starts to rise, then the circulator will start to slow down and get closer to our prescribed Delta T. Now, we get to a 20-degree delta, 180 out, 160 back, zone 2 kicks in. Slugs 70-degree water back to the return. Supply's getting 180 because that's what the boiler's doing, but all of a sudden, my return temperature starts to drop. Circulator starts to speed up. All right, so as that circulator starts to speed up, it wants to get now to an average of 160 degrees on the return side. So you might see a zone coming back at, say, 165, and the other zone coming back at 155 sees the 160 as the return as the average. So what does that mean to you? What's going to happen is the zone that's getting the 165 coming back, meaning it's overflowing, just means the zone's going to get satisfied maybe a little bit sooner. Got a few more BTUs per linear foot coming out of the baseboard. And then that shuts down. And then the circulator is going to slow down again and then slow down again based upon the Delta T of that last zone still running. So it's going to look at an average. So Joe, thank you very much for that question to really differentiate between the two of them. And then, of course, the other thing about the Delta T is it's going to change speed based upon how cold it is outside. So how many BTUs can jump off the train, so to speak, into the space itself is how many BTUs are leaving the space. Whereas Delta P has no care about what the temperature is outside. It's just going to try and shove as much water as it can out to the zones always. So same flow in February as in October, whereas Delta T is going to change it continuously over the season. So excellent, excellent. Thank you for that question. Another question from Mark. Does a Delta T circulator help a lot if you come across an oversized boiler? Oh, yeah. Especially in the cast iron world. If you're looking at cast iron, a high mass boiler, it can definitely help you out with that. It can actually start to minimize the short cycling of the boiler itself and drop it down quite a bit, in my opinion. So, because if you have a zone that only needs 1 gallon a minute, that circulator is going to slow all the way down to send out only 1 gallon a minute. And if you've got 150,000 BTU boiler sitting there, bangs up to 180 degrees and sits there at 180 with a large ton of cast iron to heat it up, how long does it take to cool down when you're sipping BTUs out of that boiler? It takes a really long time to cool it down. And then by the time it cools all the way down, then it fires back up again. You got it nice and cold. You get a nice long run time. So nice long run times, nice long off times. That's what we like to see to gain the efficiency of the system and get the comfort out of it. So Delta T can definitely help in that way. Anything else out there, Rickster?
No, that's pretty much it.
Okay, let's see. that was printed twice. Okay. When speed changes based on delta T, so will pressure change. Yes. Okay. All right. So let's say, all right, it's 8:15. I was going to go over point of no pressure change and pumping away. Should we still do that? Being that we're already 15 minutes over um, our allotted time, so to speak. Oh my God, trivia question. Yes, thank you, Rich. Thank you. Holy cow. Oh my God, we did not do it whatsoever. Because it was such a crazy night jumping back and forth between the two of them. I needed to get into that. Um, Actually, I'm having a problem in the website was not working for my wheel. I found that as I logged in tonight.
Thanks to
Um,
wheels.
yeah. I can't get, oh, nope, I can't get the website has been crashed. So I can't get to that in there today. So we're gonna have to do 2 giveaways next week. So I have a list of names from our week 6 and the week 7. Yeah, darn it. And hopefully, let's see here.
Yeah, but the
Uh,
question is about this week's trivia question. You have that.
I do have that. Let's jump ahead and take a
Don't give
look
it
at that
away.
real fast. No, not at all. Not at all. So here it is. So the trivia question of the night. So as you can tell, most of you, didn't get to see too much of the PowerPoint, but we were using Risky Business tonight. And Miles Dalby, in case anybody was curious, was Tom Cruise's or Joel Goodson's one of his friends that just created all the havoc for him and messed everything up for him. So that's where I got my name, Miles Dalby, from. So, as the contents of his parents' entire house was taken, Joel Goodson also had an interview with an Ivy League college during this entire process that was going on at the end of the movie. What was the name of the school he interviewed with? So that is our question for today. I will write them down. I do have them here, and we'll just have to give away 2 things next week, maybe 3. I think I got a bunch of stuff I just need to get rid of. Well, I think I'm just gonna next week for our last class. I think I'm just gonna clean out the closet so I don't have to carry it through the fall. So if you know the name of the school, type it in there. So this way I can give some stuff away next week. It was at first it was just like I had to think about it for a second, and you'll go back without even having to Google it. If you were to look at some pictures, you might see it on somebody's shirt. So that's the only hint I'll give you, Rickster. So anyways, so
Got some answers coming in.
we do.
All right,
All
Joe.
right.
Hey, go ahead. We can
No, no.
catch the questions as we go. So
All right. I wasn't sure if I should jump in here or not. If we wanted to play around.
I had one
Uh,
yes to your question. So anybody else, you guys want to do the point of no pressure change or not?
okay. Yeah, if you've been to some of actually, the last time we did it was probably back in May,
There's another one. There's
maybe
2 that
maybe
say they
earlier.
want to do it. There's 3.
Okay, all right,
All right,
let's rock and roll. So,
do
got
it.
some new slides, something different to take a look at with the point of no pressure change. So, right here is what we consider the point of no pressure change. Right there, where our expansion tank is tapped into our system here. All right, and you can see it down here if we throw this pressure gauge down here. That's our point of no pressure change. But what can change the pressure at the point of no pressure change? All right, which is quite interesting. So we have to stop and think about that for a second. What is going to change the pressure at the point of no pressure change? There are 3 things. All right, so let's see here. Fill valve. What do you mean, Roger? What do you mean by fill valve? So fill valve is partially correct.
That meets
But the
one of the
fill valve,
answers. Yeah.
yep,
Yeah.
it is. All right. That is going to be add or remove water from the tank itself. Yes. All right. So if we take water in and out of that tank, change the pressure, change the fill pressure in the system itself, we're going to change the pressure. Exactly right. All right. The second half here I see popped up from Philip here.
Philip.
Yes.
Yeah.
Okay. Exchange, add or remove air from the tank. Man, we're doing it right in order too. Like you guys
Yeah.
have done this before.
What's the next one?
So the third one, a lot of people forget the third one. They get this one, they get the first 2 all the time, but the third one is just all of a sudden it's one of those aha moments like, oh, duh. You know,
Yeah.
slap your house right in the forehead there. But the third way to change the pressure at the point of no pressure change, heat up or cool down the water.
Yeah.
All right. And as we heat up the water, hot water takes up more volume than cold water, your pressure goes up. So those three things are the only three things that can change the pressure at the point of no pressure change, which stands to say the circ can't do any of those three things, can it?
Right.
All right. The circulator. All right. One of the things I always try to talk about when talking about circulators, it's a pressure differential machine. All it can do is create a pressure differential. It cannot create pressure. It just creates a differential. We have to remember that. It cannot create pressure. A pump can. A circulator doesn't. Okay. So so the point of no pressure change is not created by the circulator itself. So we want to talk about where do we place the circulator in our system. All right. So this is what we talk about, that point of no static pressure change, right there where the expansion tank is tapped into our system itself. But also remember that the entire system, the volume of water that's in there, it's a fixed volume. It's not going to change. Okay. The only reason for water to change is if water leaves, right? So, but if we imagine no leaks in our system, completely filled with water, air is completely taken out, we don't have we're not going to see any pressure changes in our system, and we're not going to change the air in our tank itself. Okay. So we don't want to pump towards that expansion tank because the circulator, all right, that pressure differential, the circulator looks to the tank as a reference point on what it can do. That's what the circulator is doing in reference to the expansion tank. It is using that expansion tank as a reference point. So let's take a look at our system for a second. So let's imagine here we've got a boiler in the basement space. We're going up 2 stories to an air handler or maybe a piece of baseboard. If it was a piece of baseboard, we'll drop that down a little bit up on the 2nd floor. And we see the elevations that we have here. So I want to point out a couple of things that we have. You know, right now, let's take a look at the static pressures in our system. Downstairs, 12 psi. It's 12 psi because our expansion tank is at 12 psi. We filled our system up with water. Our fill valve set it for 12 psi, and then we took the fill valve out. All right, so that's disconnected from the system itself, but we still put 12 in there. All right, let's take a look at our readings all over the place. When we look at the height of the structure, all right, at 18.5 feet high, and our conversion to psi of 2.31, we see from the highest point of the house, there will be an 8 psi drop or an 8 psi add on the way down. Way up, 8 psi drop. So if we were to look at that high point of the system itself, if I have 12 downstairs and I go up 18.5 feet, if I were to put a pressure gauge at the highest point of the house itself, it'll read 4 psi. That's good. That's what we're looking for. We want to see 4 to 5 psi at the highest point of our house. That's what our fill pressure is for. So to make sure that we maintain that positive pressure at the high point of the house. Now, a couple other points I want to take a look at is either side of the circulator. We take a look at either side of the circulator with the circulator in the off position. All right, so therefore it's a 0 psi differential. We're going to have 12 psi on the suction side, and we'll end up having 12 psi on the discharge side of the circulator because it's not moving, it's not spinning, it's not doing anything, it's not creating a pressure differential. So when you look at this picture here, this is ideally what we like to see. We like to see 12 downstairs, 4 upstairs. We're good to go. Now, let's go ahead and turn that circulator on. And once we turn that circulator on, and this circulator happens to be a 4 psi differential circulator, let's take a look at the readings of the circulator. All right, at first, the discharge side of the circulator is going to be 12 psi. Why is it 12 psi? Because it's using the reference of the expansion tank. Where is the expansion tank in the system itself? We're pumping into that expansion tank. I can't pump water into it, right? No water can go into the expansion tank. If I were able to pump water into an expansion tank, what would be behind it? Meaning where that water was. and we can't create a vacuum. All right, we can't magically add air into the system either. Remember, we purged all the air out. We don't have a fill valve in here. So water does not get pumped into an expansion tank because of the pressure of the air on the other side is keeping the water in the pipe also. 12 psi air is on the other side of that bladder. So we're using the reference side of that. Now, since the circulator is a pressure differential machine and it's using the expansion tank as a reference point, and it happens to be a 4 psi differential, the suction side of the circulator has to be 8 psi. 12 minus 4 gets me to the 8 psi that's there. And you might look at that and say, that's okay. As long as I can still move water, it's going to work just fine. But remember the height of this structure. And the height of this structure had an 8 psi drop. So with an 8 psi drop, we go ahead and take a look at our pressure gauge up on the upper level of the house. We have the potential to see 0. We wouldn't see vacuum, but we could see 0 psi. If we see 0 psi in the upper level, then we can't move water. Water's not going to move around in a circle. All right, that circulator's not, it's circulator spinning, but it's not moving anything. All right, that's the issue that we can run into. That's the potential that we can run into. Now let's take a look at these numbers and move it to the other side. All right, so if we move the circulator pumping away from it, still uses the expansion tank as a reference point. Let's take a look. Here's everything that we saw before. Ideally, this is what we like. It's identical. All right, when you take a look at the pressure readings, but the circulator is now on the discharge on the discharge side or on the suction side of the circulator is where my expansion tank is. So we're pumping away from that tank right now. And it's just moving it over a couple of feet to the other side. So we see 12 and 12 down here on either side of the circulator and 4 psi upstairs. Now we go turn that circulator on. 4 psi differential circulator. Since it's using the expansion tank as a reference point, the suction side of the circulator is going to be 12. The discharge, because it's a pressure differential machine, is now going to be 16 psi on the discharge side. And if we take a look upstairs, we're now going to see 6 psi upstairs. You'll never run into an issue in heating the upper levels of a project. What if they went ahead and moved this up and put another floor in here? There's an attic above this that they finished off, and you needed to put another zone of heat upstairs. All right, and you were pumping on the return side or pumping into the expansion tank is where you run into those issues, especially when you start getting higher and higher with the system itself. So if you were to put your circs on the supply side, pumping away from that expansion tank, you'll always have the pressure differential of the circulator added to our system rather than subtracted from the system when we put it on the return side. Now, that begs the question, why from decades upon decades upon decades did we put the pump on the return? Was it because it was just a BAP? Big ass pump? And big ass pump just means in stature, right? Our big old 3-piece circulators were on the return side for decades. And the reason why that was able to handle being pumped on the return side for so many years, and even if you took a 007 and pulled out that big old 3-piece circulator and put a 007 in its exact same place, and it still worked for decades after that. The reason why it worked is because that circulator was not a 4 psi differential. It was like 1.5. All right, so a 1.5 pressure differential. Let me go back and put the pump on the return side, and let's take a look at our numbers. All right, not that one up there, but now we go ahead and change this to just 2. Change it to 2 psi so we can make the math easy. So we see 12 on the discharge side of the circulator because the expansion tank says so. The suction side now says what? If I have a 2 psi circulator, we're going to see 10 here. If I have 10 on the suction side of the circulator, I have an 8 psi drop as I go up. I can see 2 psi on the upper levels. So that's why a lot of these flat curve circulators work so well. B&G 100, Takeo 110s, very flat curve circulators, low psi differential circulators. Steeper the curve, the larger the psi differential that you get out of those circulators, and that's where we can start running into issues on them. So
Let's answer a question for Jordan here. Jordan's question is, how did we determine in this scenario that the pump made a 4 psi difference? Well, what we do is we go to that circulator performance curve, right? And we go to that vertical, the y-axis, and we say, what is the shutoff capability of that pump in feet of head? And we simply converted that with 2.31 as our constant. We converted that back to psi. Jordan, hopefully that helps you. That's how we knew what that pump would do.
right. So that's all. We just pulled the pump curves
Yep.
and found the psi differential compared to foot ahead. Right. Exactly. So another question comes in from Milek. Is it a difference if the expansion tank is on the supply or return? You mean if I were to move the expansion tank rather than move the circulator?
That's what we were just showing you on those slides. We
Well,
had
we
one scenario.
moved the pump. We moved the pump here. What if I were to move the circulator? I mean, move the expansion tank.
There you go.
Same
Just
difference,
answer the
right?
question.
Yeah.
You're either pumping into the expansion tank or you're pumping away from it.
Right.
One or
So
the
we
other.
always, yeah. When we take a look at Dan Hollahan's book, Pumping Away, a lot of people have always assumed it's pumping away from the boiler. And it's not the boiler, it's the expansion tank. That's the one thing to really remember. So the boiler has absolutely nothing to do with it. It's more about where the expansion tank is. So if you had a system that was running into this issue, Milek, to sometimes move a circulator is a lot harder than maybe even moving an expansion tank. But I would also say it might be even easier to change the circulator to a low psi differential circulator or flat curve like a 007, 0010 style circulator rather than the steeper curve circulators. That's probably the easiest way to run into that or to fix this. Explain the 6 psi upstairs again. All right, so let's go ahead and take a look at that again. All right, so we have 16 here. Oh wait, do I have a typo?
No. What's 16 minus 8? You have the column
Oh,
weight of
yeah.
water. There's always going to be a reduction there,
Yeah.
right?
Yep. The 12. Yep.
Plus you have friction loss. But coming back down, now you have the weight. So think about that. We keep talking about Ferris wheel, right? Going up, everything helps us go up because of what's coming down the other side, but you can't forget that you have resistance, you have friction loss of the water running through the pipe. The 6 psi is an estimate based on those two principles. Hopefully that answers your question, Terry.
Okay. And I just so happen to have this display behind me that I built last year, or not last year, but actually this year. And let me pull the camera in a little bit closer so I can go over the actual working display here so you can actually see it operate. So what we're looking at here, I've got our 006 E3 circulator here. And this is our, I used it just because it had a composite volute and I didn't have to worry about rusting and or anything happening inside the pipe here. I got a pressure gauge on either side of the circulator. As we come out, this is our discharge side of the circulator. We go up this way. I have a globe valve here, and I put this globe valve here just for to create pressure against the system to simulate a zone. Then I come across the top and I hit my air eliminator and we come back down into the suction side. Now across the middle here is just a couple of ball valves. I've got a blue handle, I got a yellow handle, and right behind this small expansion tank is just a copper T. All right, it's just a threaded T. I have this valve, this expansion tank threaded in there. So if I have this valve up, all right, that means this is shut off, this valve is open, and right now I'm pumping away from the expansion tank. When I swap them, now I will be pumping into the expansion tank. So the expansion tank is teed in here. This is shut off. So now it's just pumping into, and imagine this is my zone in my system here. So you can imagine a boiler sitting right here. Here's my air eliminator. I didn't tap in where the air eliminator is here because it was harder to isolate my expansion tank. And let's take a look. So my pressure gauges are not exact, but kind of close. Right now it reads, this one is reading just about 20.5 PSI. Yeah, they're really close to each other. So I kick this thing on, the circulator is going to run. And my discharge side, since it's using my expansion tank as my reference point, this barely moved. But if we look at the suction side of the circulator, this one dropped back almost 3 PSI. This is not a very strong circulator, okay? So now
What
this has
speed do you
dropped
have it
back. I have it maxed out.
on? Okay. Yeah.
And I'm not sure how accurate these gauges are either. I
Yep.
just know they're both the same. So it took a digger the other day. This thing came flying off the table in the middle of a training class I was doing. I backed into it. All right, so now you can see what's happening. So my suction side of the circulator had to change because the discharge side is regulated by the expansion tank. So let me turn this off real fast. Let's swap these valves. So now I'm pumping away from the expansion tank. So now it's connected on this side, isolated over here, just connected here, and I'm pumping away from the expansion tank. And when I kick this on, we take a look at the discharge side valve. And you're going to see that's going to increase upwards. So right now that has increased itself up to 24 PSI. And over here on the suction side has remained the same, hasn't moved. It's bouncing just a hair, but now we have added the pressure differential of the circulator itself to the system itself out there. So very simple display. I had another one that had a bunch of PVC pipe on it. Mr. Holohan, Dan Holohan, had given it to me a couple of years ago, and we shipped it from Rhode Island down to my home office here on Long Island, and it broke in the mail. So had to build a whole new one. So there's the new one, and there it is.
The proof's in the pudding, folks.
Yep. So when you could see it work like that, that's what
Hey, Dave.
Yes, sir.
Hey, take your slide back to the air scoop where you're pumping into the point of no pressure change. Right
here?
there. Yeah. So, folks, this is where I get in. I don't argue, right? But this is where most people say that this concept is hogwash, because they're saying that when that circulator turns on, it's going to see the pressure gauge. In fact, you guys understand that the pressure gauge, the most important spot for the pressure gauge to go is at the point of no pressure change. Okay, so understand, see that PG? That's depicting a pressure gauge. So everybody swears that that pump, I don't care if it's a big ass circulator or not, they swear that that pump, when it turns on, is going to cause that pressure gauge to go to the right or increase in pressure. Can everybody understand that, right? Because conceptually that makes sense, right? The question you have to ask the person who is in doubt is, the only way that pressure gauge would actually change its position is for Dave, take your pointer and see that little drop pipe coming out of the air scoop and going down to the expansion tank.
Mm-hmm.
Point it right there. So you folks have to understand, water would have to come down that pipe in order to increase the pressure at the pressure gauge. Everybody goes, shake your head, yes, that's what would it have to do. Ultimately, this is where you get them. Where would that extra water come from to go down that pipe? And that's why, Dave, I show the bicycle chain, right? You
Mm-hmm.
got to understand the water is a macromolecule. You can't pull it apart and you can't compress it together. So if you understand that, there's no way water can go down the pipe in order to make the pressure gauge change. So hopefully that helps you better understand this whole mystery, because I guarantee you, Dave and I and John teach these classes all the time, and people just shake their heads. They don't understand why that pump can't change that pressure gauge. And Dave just showed it to you in real life, and some people still shake their head. But I want to make the point is the only way that pressure gauge is going to change is for water to actually go down that little pipe. And it can't, because where's it going to come from? The system is full of water. It has no air in it, blah, blah, blah. So once you get your head around that, good stuff. So
Awesome. Sorry, just writing down some names here for our trivia
good,
winners.
good. Yeah, some questions. Larger circulators have the 1/4-inch tappings. Absolutely, Jay. But guess what? There's plenty of product out there that you could put as isolation flanges on each side of a pump that have boiler drains. You just got to make sure that they'll be in the open position when the valve is in the open position. And you can actually build these little whips and do a single pressure gauge is much more accurate than 2 pressure gauges. So if I was going to build one, I would have a nice high quality within the realm of the pressures of the associated system, and I would get it liquid filled. That way it doesn't bounce a little bit or anything. So you're going to spend some money on it, but your accuracy, what you get out of a single gauge in lieu of 2 gauges is you don't worry about the accuracy plus or minus. Every manufacturer like Ashcroft or in Marsh or anybody else that makes gauges always give you a plus or minus 3% or 4% or 6% or whatever it is. If you can imagine, if potentially you had one gauge that was minus 4% and one gauge that was plus 4%, you would have an 8% error on your readings. We don't want that. So we want a single gauge. That way we get a higher accuracy on that. So
Yeah,
hopefully
just like I was shown with my gauges. You know, they're not that accurate when I turn them off. So
there's a
looks like
little
they're
bit of difference, right?
a
So
little bit of difference between them. So yeah, you guys can't see it, but I can because I'm literally 2.5 feet away from them. So
yeah.
um, yeah, it would be so much better to see a single gauge and you just open the valve from one side to the other. But this is what I had laying around the garage, and you know when I built this back in, gee, I think it was April. Nobody even wanted to walk out in their driveway. So
Mark's he's just clarifying. Yes, Mark, pump away from the expansion tank. Whatever way you can do it, don't put 2 expansion tanks in the system unless they're both paralleled into the same point within the system. So some people have I'm going to put an expansion tank here and there and there. Don't do that. Okay, I'm not saying that you won't get flow, but you're going to freak things out a little bit. So again, pump away from where the expansion tank goes into the system.
perfect. There we go. Yep.
Ah,
All right. Yep. That's right. I was going to pull up the display. I forgot to show this famous scene of the 928 going in the water.
Porsche.
Yes, I think everybody cringed when they saw that happen, right?
Yeah.
All righty. Any other questions out there, people? Please ask away. I know we've kept you here for a while already. And again, as somebody said earlier, what else are we going to do on a Wednesday night right now? So please ask away anything that you got. Or,
We
so
still
that's
got
what.
80 people online, so you folks whip it out. And like Ted Nugent said, if in doubt, whip it out. Ah, Mark says his wife passed out. Cook, Mike. Hey, good to see you, Mike. Take care.
Enjoy, Mike.
Dan Cook, I have a question for you. So let's talk about something that's come up that has to do with product. So Dan Cook, at your convenience.
Just not right now.
Not right now. Helen Grun. Scotty, how are
Scott,
you?
good to see you, man.
Shorty.
Milik, enjoy, brother.
Milex having a beer. Good.
That's right. That's right. Let's see here. We can always watch the recordings of the class. Yes, you can, Roger. So yes, the recordings of the classes will be on Mechanical Hub's YouTube page as well as our YouTube page. Whoop, lights went off in the room. 2.5 hours since I've been online.
You gonna wave and make some? You gotta hit the switch, or
No,
you
it's a
just make?
timer.
Yeah.
Yeah, no,
Oh,
it's a regular timer. Also turns the
yeah.
fan off. So
Yeah.
I'm in an unconditioned basement right now, so it gets a little hot down here. So
Terry, no, not yet. Terry's asking if we have a residential Delta T pump that has Bluetooth. Not yet. Keep your ears peeled though.
yeah, we'll see what happens in the future. Aurora, you put the answer in the right spot, so I got you, Aurora. And those of you, and when we do the winners for next week, I will contact you afterwards to find a mailing address to send you some of the stuff. So, Mr.
Yeah.
Miller, soon, my man, soon. Yes, we will see you.
When's that? Is
Yeah,
that a
who
different
knows?
Mike? Is that a different
know.
Mike Miller?
No, I think that's ours.
That's our. He doesn't
Should be
normally
our
call
Mike Miller.
himself Michael.
Oh yeah, maybe not. Let me see here. I have the attendees list.
Chris is looking for combustion analysis. We can get one of our boiler guys in here to do that, I would imagine. Good. That would be a good topic for sure. Smart
That was our
plugs, is
Mike.
there a
That
way to
is our Mike
change
Miller.
timing?
Yes.
No, Jordan, you can't change it's a fixed timing, 5 minutes on, 10 minutes off. Down the road, we might give you some adjustment. But right now, Jordan, it is fixed.
So yeah, and just so everybody understands, that's our domestic hot water recirc timer, the smart plug. It is set for a 5 minute on, 10 off, but it's that learning schedule that it learns of somebody's schedule in their house on when they use hot water in the house. Believe it or not, 5 minutes is just about the right amount of time that's needed in order to move water in most homes. In some of my calculations that I've experienced over the past in residential settings, we see it might be 4.5 minutes to move the water, maybe 5.5 minutes, but it also turns on way before somebody's looking for timing. So I would like to know why you're asking for that time change. What have you experienced, or is it just something that you're thinking of in your mind right now, Jordan?
Well, I'm with him. I'm with him
And this is
100%. You know, we need
what's that?
we need adjustable on times. We need adjustable off times eventually. So, and there's all kinds
Yeah,
of
there
reasons
are
for
there
that.
are
Yeah.
yeah, there's a lot of little reasons for them that we can do that, but I'm also curious as to why you're asking too. Are you running into an issue on some of your projects?
Pump's running longer than it needs to. That's the biggest one.
Well,
And it can
it's not
stay
running
off a lot
24/7.
longer than 10 minutes based on
True that.
insulation,
True that.
temperatures, and all that good stuff. So eventually we were trying to get them there, but that big wheel turns pretty slow. So, in fact, we could actually show them, the folks that are hanging out, we still got 67. They want to see the app. I'll go through it with them if they want. That's actually, we actually had marketing deliver it. Did we do the DHW app on this summer session?
I
We
don't think
haven't.
so. No.
Well, you guys, we can save it for another time, but it's a
Yeah,
simple
it'd take a
little
lot of
app,
time to
and
do that now. Yeah.
yeah, yeah.
So yeah, that would be it'll take a lot of time to do that. So we may save that for our fall sessions. I think we're all set for next week's session class that we have. So John, I got your question. I got your statement there. So I like it. All right. Yes, we could easily bring that in and get some of our venting guys available to us. I know maybe that much, and that might be a lot on some of that stuff. So where I could teach it and whatnot. So so Joe
Joe's got
Walker.
one on. He's saying he can't get Takeo available where he's located. Well, you know
Well,
what?
then move.
You know, tell us where you're located, and we'll point you in the right direction rather than answer that question. So, Yeah.
You got to move, brother.
Yeah.
Well, get them online too, so
Sure.
that's why I see a lot of that stuff. So, all right. Let me pull back to here. And yes, this was for supposed to be earlier, way out of order today. So the trivia answer for tonight. Okay, so get them in there if you haven't gotten it in just yet. So get those trivia questions in, trivia answers in there. What the heck happened to my screen here? Went flipped over backwards. Look at that.
No, it looks good on this end.
I meant my questions here.
Oh, okay.
Oh, there we go. The trivia answer for tonight, darn it, I did it again, hitting the wrong button, is Princeton. Princeton University is where Joel Goodson planned on going to school. So that's what I meant by trying to find that picture. Oh, he's in Australia. All right. Yeah, that's going to be tough there for you. Yeah, I don't think we're selling too much residential overseas, unfortunately, there. So, yeah, it's going to be tough to get Takeo product out in Australia. Well, but we're working on it. We're working on it, but greatly appreciate you hanging out with us tonight. So,
Well,
um,
let me go to his question then, Joe. As far as what you're asking about, remember how I listed 5 different auto adaptable type uh, uh, modes of operation? All of those work, right? I mean, they all kind of do the same thing. There's some different little small variants on them, but remember, most importantly, it's a rare time that they're applicable for most systems. Okay, in North America, I realize you're not there. You're in Australia, so I get it. But look, try to keep in mind of what the piping schemes I showed you, the different piping layouts, right? Again, if you're doing home run systems, then that feature that you're speaking of in your question is not applicable for you. Okay, so that particular pump has 2 other modes of operation. You're going to pick one of those that makes the most sense rather than that automatic mode, because most of the time those auto modes don't make sense. Hopefully that helps. So.
excellent. All righty. All righty. Oh, so let's see here. Next week's class. What do we got going on next week? It's going to be a good evening as far as I'm concerned right now. And basically, we don't have a set topic. I think it's going to be a wide open. We're going to have a lot of our past guests that we've had on. So we're going to do like a big old roundtable discussion. So instead of just looking at the 2 of us or the 3 of us, I think we're all going to be on at the same time. And we're even going to have some new people, some new guests also join us there. So topics are whatever you guys want to bring up. Who knows? Maybe the future of hydronics. What does the industry see? What does the manufacturers see? What do reps see as what the future is going to be? So that could be one of our topics that we can talk about that for next week's class. So we're going to leave it wide open and have a lot more friends hanging out with us. It's going to be the last one out there for the summer. So yes, the summer's almost over. Here we are, the first week of August, almost done. And we still have quite a few people hanging out with about 60 of us, and Mr. Messenbrink is still with us too from Mechanical Hub. So if you've got anything to add, John, as we are ending our evening and approaching our last one. Actually, it looks like we've had a bunch of questions pop up. But if you've got anything to add also in there, John, we might as well bring it up now.
No, I'm good. You guys are doing a great job, and I'm looking forward to next week. It should be exciting with some new guests. So yeah, stay tuned for next week.
Yes, I'm not sure of the guests yet. So John was working on that. So hopefully he's kind of working on it while he's away right now too. Probably
We'll
not.
see. We'll see. Yeah.
I think he put his feelers out already yesterday and today before he left the house. So one of the questions from Philip, question in the hydronic design heat loss. There was an order form from AHRI to place the orders for the calculations. I have gone there, and you can't find them because AHRI and IBR, they keep on. Who owns them now? It's merged into another.
AHRI.
It's AHRI.
Mhm.
So I will look into that a little bit further for you there, Philip, and we'll let you know. I remember finding it last year sometime in regards to that. So I will find that answer on where the H22 guides are and order forms. So
Dave,
I'll find that website link.
if it's something that's a PDF, can we just send it to somebody, or is that like plagiarism or whatever?
Well, the form that we share, we're allowed to give away.
Right, because that's got Taco's name all over it and stuff. But what he's looking for,
Well, we
do
were
we have
given, yeah, we were given the rights to share that in our training classes.
okay, all right, good.
So the form that we have, you can print up as many copies as you like. But I will also, I know there's a link. I just got to go find it for you. It was a little bit of a challenge to find it the last time I looked for it. So I will look that up for you, and I'll probably send you an email, Philip. So awesome. Where might I find past webinars to watch? Aurora, that's going to be on Mechanical Hub, as you see here in the top right of the screen, Mechanical Hub YouTube page, or the Taco Comfort Solutions YouTube page. You will see a tab for the Taco After Dark sessions, and you can go back and watch them as many times as you like. So when you miss us tomorrow, you can go and watch it again. Let's see, Jordan, potential introduction to commercial. Oh, okay, so a couple other classes. Oh, drag Mr. Miller. I like it. I like Mr. Miller. So Rick and I can take some time off. Actually, Rick likes to dabble on the commercial side of things. I'm strictly a res guy. So we'll let Rick hang out still. And yes, school's out for the summer. Definitely, Gary. All right, I'm not seeing any other questions coming in. Oh, of course, Jordan throws another one in right at the last second. He beat the buzzer.
When radiant is secondary heat source, working with forced air, which is the primary heat source? Do you calculate your heat loss differently? No. Those two numbers, whatever the load is the load. I mean, some of it's going to be radiant, some of it's going to be hydro air, or just a typical furnace, but the load is the load. Now, again, if they're both hydronic, then those two numbers will be this put together. If the furnace is doing its own thing and the radiant is just supplemental, then you'll throw a number at it, like probably for supplemental heat, probably the range of 15, 20 BTUs a square foot is more than enough. So, Jordan, I hope that answers your question, but you're saying forced air, but is that hydro air or is that a furnace with, an atmospheric burner or a separate flame, I should say?
Yeah, a lot of my experiences is radiance thrown in as just a floor warming aspect, right? So you're just taking the chill off the floor, so it's, so to speak, secondary heating for the radiant. If you have the option, I try to make the radiant floor heat the primary heat source. And because if you needed secondary, as in you needed supplemental heat, then you turn on the furnace when it's getting really cold outside. But if a lot of times if it's just a floor warming aspect, where the furnace is the main thermostat throughout the entire house, and you only got little areas that have radiant floor, then yeah, you just pick a number to do it. There is not a set BTU per square foot that you would use for a floor warming aspect. You just pick a number, and like Rick was saying, 15 is more than enough. You throw in a slab sensor, so this way because the furnace would satisfy any heat in that room itself, so you need to be able to turn that radiant on.
Terry's got one here. Unless there is a radiant floor with slab losses, just Terry, good point from the standpoint of what we call back losses or edge losses, and the combination of both those. Most of the manufacturers that make some kind of software will take care of that one way or another. Some actually calculate it based on the ground temperature and the slab temperature and the R value that's the thermal break between those two. And some of them just throw a percentage at it. They just take a round number and say any of the actual load that's on the slab itself, you're going to lose 20%, out the edge and out the back. And some people do it that way. There's different software manufacturers, or different manufacturers are going to have those software manufacturers actually put something in there. So I personally like to see an actual calculation based on slab temperatures and moisture content, all that other stuff. So anyway, that's something you can look into as well. But yeah, don't forget it. You will have back losses and edge losses, and the bigger the R value, the better the insulation that you do is going to lessen that to a great extent. So
Excellent. All righty. Another one here from Roger came in. What about snow melt? Do you all use glycol with a heat exchanger? Oh, heck yeah. Well, maybe not necessarily do you need a heat exchanger, but you definitely need to use glycol. Um, in the system itself. So this way we're not freezing up when the system's idle or not being used at all. So you don't get slush in your pipes and frozen pipes. So yes, you need to use antifreeze at that point, putting a glycol in there. Whether or not you need or desire a heat exchanger will depend upon the system itself, meaning the size of the boiler versus the size of the snow melt system. Is it a dedicated boiler? If it's a dedicated boiler, then I wouldn't even think about a heat exchanger. You just glycol the whole thing right then and there. Just make sure you maintain the glycol levels, the acidity levels, things like that. Treat that water and test it as often as you can. So small jobs, throw a small heat exchanger on it. Maybe you're just doing a sidewalk snow melt and you've got a big boiler already in the house. And this way you just isolate it. I don't need to fill the whole house with antifreeze. I don't want to. I'd rather just isolate it just to the snow melt side of things. So there's a lot of variables, a lot of it depends. And what I find, we way over antifreeze here in the East Coast in a lot of areas,
no,
meaning
everybody
percentage
does.
wise. Yeah,
They
percentage wise is way over. Yeah.
they don't understand the two different actual columns. So they think that they're worried about sending slushy around as a normal state of a design condition, and they're not. So in fact, I would challenge anybody that's still listening. What do we got? 53 people. Take a look at if you're glycol people and you use glycol and stuff. I will challenge you to find out what's the thickest glycol mixture you will ever need for a typical HVAC system, and send us your answers as soon as you can, and we will challenge you on that for the most part. Gerald's got a question. Absolutely, hot tubs. If you got a hot tub and you put a heat exchanger on that thing, and you got a hydronic heating system, you'll heat that thing. You don't have to put electrical strip. You don't have to put a little gas-fired boiler on the side of your hot tub or anything like that. Again, you got to size accordingly because you've got a load that's considered for that hot tub. But I got a buddy here in Salt Lake that does it, and every time we go over there, it's champagne and hot tub time, and it's all done on a heat exchanger and a condensing boiler. So I know that because I helped install the whole thing. So
I've got a couple of answers here. First one comes in from remote Alaska. 50% is standard in glycol.
understand, John Allen. Remember, I'm an Alaskan. I spent 33 years there. If you're worried about the fluid in the pipe ever expanding to the point of breaking pipes, and keep in mind that's what most people are concerned with, you never need more than about 36% glycol. Now, if you are always going to pump really, really cold, say for instance you're going to pump 15-degree glycol around a system all the time, and you wouldn't want that glycol to turn into a slushy. You don't want any ice crystals. That's what the freeze column is for. Everybody uses the freeze column because they misinterpret that to say, I don't want my pipes to freeze. What that means is ice crystals within the fluid. If you're okay with that on a power outage, and of course when power comes back on, the pump comes back on, you'll actually move things around slowly, make up for it and all that stuff. So understand those two different columns. You have a freeze column and you have a burst column. Most people in the HVAC business that actually do heating and snow melting and all that stuff are concerned with the burst column, not the freeze column. And you'll see about 36% glycol is all you'll ever need. Get you down to about minus 50 Fahrenheit. So.
Yep, just got to look at the right numbers. Yeah, we don't. Yeah, ice crystals in the water doesn't mean it's frozen. Remember that. So it's
Yeah, it
just
means
ice
it
crystals.
won't expand and break your pipe, is what that means. And again, don't take my word for it. Taco doesn't sell glycol, right? Go to the people who sell your glycol and make your glycol and look at their documentation. I think you'll see the same thing I'm telling you.
Here's a good question from Jordan. Could you effectively have an outdoor pool heated by radiant floor and walls, or potentially couldn't keep up? Yeah. Um, I think I did the math once, and it was next to impossible. I don't think I could pack enough pipe in there to try to heat a pool, and then therefore the boiler size was just monstrous too at the same time. So, I don't know if did you ever do any math like that? Work on it, Rick?
Yeah, because we did pool exchangers all the time. So the way the
Well,
math
no,
works.
meaning radiant
No,
embedded
no,
in the
no. I'm
in the
telling you,
gunite.
I
Yeah.
would never try it because of what I'm about to say.
Oh,
Okay.
okay.
Uh, the actual load on a pool is about 12 BTUs per square foot of surface area per degree differential, and that has no wind strippage factored in there. So when you figure out what that number is, and then you figure that's what your load is, right? Under a design condition with wind and all that stuff, most of the time you'll never be able to actually, through conductivity, transfer enough energy into the pool to maintain it. Now, if you cover it up, you insulate it, and maybe you could do, but like Dave said, there's not a lot of people out there that have run those numbers and know for sure. The loads go up dramatically. For instance, say you wanted that hot tub to work in the wintertime. Okay. So let's say it's 30 degrees outside and you've got a 30-degree outdoor temperature and you've got a surface temperature of 105. What's your delta T times 12 times the square footage? You got some numbers there based on BTUs an hour, and that's really hard to transfer that much heat at a given time just by conductivity. So yeah, I wouldn't do it if somebody just asked me unless I could find somebody to actually test it. Okay.
Hmm. I know I was experimenting a bunch of years ago of putting tubing in the concrete deck around the pool
Right,
and using that as a solar gain to
right. To
dump
heat
into
the
the
pool.
pool.
That
And
works.
what's that?
That
Eh,
works.
Right. But if you want pavers on top, then don't even think about it. I
Yeah,
think it just cut it down at less than a quarter of the BTUs I can get out of it. So
yeah.
that I was going to do, but we wanted to do pavers around the pool. So um, yeah, I didn't put the pipe in. Alrighty. Okay. I think we are just about done for the evening. Wow, just over 2 hours tonight.
Yeah. Well, the 52 people that are still with us, thank you so much. And
Thank you.
everybody that joined us. Mechanical Hub, thank you very, very much. Appreciate
Greatly
you
appreciate it. Yes, and greatly
putting
appreciate you guys hanging out with us, and we know the value of time. We talk about this all the time, and we take that gift of your time very seriously. So we do
indeed.
truly hope that we give you what you guys are looking for.
Yeah,
One, the entertainment value. I have a good time doing these things, and two, walking away with some knowledge to just get a little bit better. Yes, Miles. And if those
yeah,
of you that are not sure who Miles is, it's this guy right there.
yeah.
That's Miles.
He's
All right, if you didn't
also known
remember.
as Booger.
As Booger, yes,
Yeah,
from Revenge of the Nerds. Yes, I know. My wife said, "Who's Miles?" And I said, "Booger." She's like, "Oh, okay."
yeah.
So awesome, gentlemen and ladies that are out there. Greatly appreciate it. Next week, same bat time, same bat channel. We'll see you for the last Takeo After Dark.
Later,
Enjoy,
folks.
y'all.
Catch
Later.
you
Have
later.
a great one.
Thanks, everyone.
Thank you, John. Catch you
Thank you.
later.